Carbon. Carbon has a rich history, diverse properties, and numerous applications across various fields. Here is an overview covering its history, properties, application, uses, experiments, DIY projects, and waste management. History. Carbon has been known since ancient times. Early humans used it to create charcoal by burning wood in the absence of oxygen. The term carbon is derived from the Latin word carbo, meaning charcoal. In the 8th century, the immense nature of carbon was recognized and studied extensively by chemists. The discovery of carbon as an element is attributed to ancient civilization. However, the modern understanding of carbon elements, nature, and its properties emerged gradually through the work of various scientists over the centuries. For instance, ancient civilizations. Humans have been aware of carbon since ancient times, primarily through the use of charcoal, which is carbon obtained by burning wood or other organic matter in the absence of oxygen. Ancient civilizations such as Egyptians, Greeks, and Romans used charcoal for various purposes, including writing, drawing, and metallurgy. Robert Boyle (1627 to 1691), an Irish natural philosopher, chemist, physicist, and inventor, conducted experiments on the properties of charcoal. His work laid the groundwork for understanding of carbon properties as an element. Antoine Lavoisier (1743 to 1794), a French chemist known as the father of modern chemistry, conducted extensive studies on combustion and oxidation. He recognized that diamond and graphite, two different forms of carbon, were composed of the same element. Lavoisier's work was crucial in establishing carbon as an element. Sir Humphrey Davy (1778–1829), a British chemist and inventor, contributed to understanding carbon's elemental nature by isolating several elements through electrolysis, although he did not isolate carbon itself. William Hyde Wollaston (1766–1828), an English chemist and physicist, discovered the element palladium in 1802 while investigating the properties of platinum ores. He also observed graphite and determined it to be a form of carbon. Henri Victor Regnault (1810–1878), a French chemist and physicist, conducted extensive research on the properties of carbon compounds and their reactions, contributing to understanding carbon behavior in chemical reactions. While no single individual can be credited with the discovery of carbon itself, the collective contribution of these scientists, along with many others, gradually shaped our understanding of carbon as an element with diverse properties and applications. Properties. Carbon is classified as a reactive nonmetal. As a nonmetal, carbon gains, shares, or retains electrons in chemical reaction to achieve a stable electron configuration, typically by forming covalent bonds with other elements. Nonmetals generally exhibit properties such as poor conductivity, both electrical and thermal, brittle solid or gaseous states at room temperature, and varying degrees of reactivity. Carbon is a nonmetallic chemical element with symbol C and atomic number 6. It exists in different forms, including graphite, diamond, furans, graphenes, and carbon nanotubes. Carbon atoms can form strong covalent bonds with other carbon atoms, resulting in various allotropes with different properties. It has high thermal and electrical conductivity in certain forms like graphite and graphene. Carbon is a relative inert but can react with oxygen at high temperature to form carbon dioxide or carbon monoxide. Carbon's ability to form stable bonds with other elements allows for the reaction for creation of countless compounds. Organic chemistry. The study of carbon compounds is vast and diverse, with application in pharmaceuticals, plastics, agriculture, and more. Carbon is central to the Earth carbon cycle, moving between the atmosphere, oceans, biosphere, and the geosphere through photosynthesis, respiration, decomposition, and erosion. Applications and uses. Graphite, used in pencils, lubricant, batteries, and as a moderator in nuclear reactors. Diamond, used in jewelry, cutting tools, and industrial applications requiring hardness and durability. Fluorinase and carbon nanotubes, used in nanotechnology, electronics, and materials science. Activated carbon, used in water purification, air filters, gas masks, and chemical purification processes. Carbon fibers, used in aerospace, automotive, and sport equipment for their lightweight and high-strength properties. Carbon black, used as a pigment in inks, paints, and rubber products. Carbon nanomaterials, used in sensors, energy storage devices, and biomedical application. Carbon sequestration. Capture and storage technologies aim to capture carbon dioxide emissions from industrial processes or power plants and store them underground to mitigate climate change. Carbon dating. The radioactive isotope carbon-14 is used in archaeology and geology to determine the age of organic materials. Carbon-based pharmaceuticals. Many drugs and therapeutic compounds contain carbon atoms as essential components, contributing to the field of medicinal chemistry. Experiments and do-it-yourself (DIY). Carbon filtration experiment. Demonstrate the absorption properties of activated carbon by filtering water contaminated with impurities. Graphite conductivity experiment. Construct a simple circuit using a pencil-drawn graphite line to demonstrate its electrical conductivity. Carbonate decomposition experiment. Heat a carbonate compound, such as calcium carbonate, to demonstrate the release of carbon dioxide gas. DIY charcoal making. Create charcoal by heating wood or other organic materials in a low oxygen environment. Carbon paper battery. Create a simple battery using activated carbon, paper soaked in electrolyte solution, and the metal electrodes to demonstrate the principles of electrochemistry. Carbon ink circuit. Design and draw a basic electrical circuit using conductive carbon ink on paper or substrate, showcasing the versatility of carbon as a conductor. Carbonation experiment. Investigate the process of carbonation by dissolving carbon dioxide gas in water, observing the formation of carbonic acid, leading to the characteristic fizzy and carbonated beverages. Carbonation experiments. Investigate the process for carbonation by dissolving carbon dioxide gas in water and observing the formation of carbonic acid, leading to the characteristic fizzy in carbonated beverages. Waste management. Recycling. Carbon-based materials like paper, cardboard, and certain plastic can be recycled. Composting. Organic carbon-containing waste, such as food scraps and yard waste, can be composited to produce nutrient-rich soil. Waste to energy. Carbon-rich waste materials can be incinerated to generate heat or electricity. Landfill management. Proper disposal and management of carbon-containing waste, such as methane emissions from landfills to minimize environmental impact. Biodegradable carbon materials. The development of biodegradable plastic and materials derived from renewable carbon sources can help mitigate the environmental impact of carbon-based products. Carbon offsetting. Carbon offset projects involve investing in activities that reduce or remove carbon dioxide emissions, such as deforestation, renewable energy projects, or methane capture from landfills. In conclusion, the unique properties of carbon make it indispensable in various industries and applications. While its versatility contributes to innovation and progress, responsible waste management is essential to mitigate environmental impact. Additionally, conducting experiments and DIY projects can enhance understanding and appreciation of carbon properties and applications.